Chapter 8, Section 7 is factoring special cases. The first special case that we've talked about is factoring the difference of two squares. We're still first going to look for a GCF if possible. Now the GCF of this first example would be a 3, and that leaves you with m to the 4th minus 25. Now to find the difference of two squares, something is dots if it's a binomial, which this is, and if the first term and the second term are both perfect squares, which they are, because the exponent here is even, which means it is a perfect square. It's evenly divisible by 2. So we're going to leave the 3 out in front and break our two sets of parentheses. Difference of two squares has 1 plus and 1 minus. The square root of m to the 4th is m squared. And the square root of just the 25, the negative sign doesn't matter, that just means it's a difference. The square root of 25 is positive 5 and negative 5. We check to see that it's not the difference of two squares again, which it's not, only because 5 isn't a perfect square. These are relatively prime, these are relatively prime, so this is completely factored. The next example, again, this is a perfect square and this is a perfect square because the exponent is evenly divisible by 2. So we set it up as plus and minus because there's no GCF. The square root of x to the 8th is x to the 4th. The square root of y to the 4th is y squared. And again, we check again that they're relatively prime and that they're not the difference of two squares. This obviously can't be the difference of two squares because it's addition, but this can because it's the difference. Now x to the 4th is a perfect square because this is evenly divisible, and y squared is a perfect square because 2 is evenly divisible by 2. So the x to the 4th plus y squared stays there, but the other one is broken down, difference of two squares again. The square root of x to the 4th is x squared. The square root of y squared is y. We check one last time. This isn't difference, isn't difference. This is, but it's y to the 1st, and 1 isn't evenly divisible by 2, so this is our final answer. Chapter 8, Section 8 is factoring by grouping. We're going to be factoring a cubic polynomial, but if there's more than just 3 terms, it's not just a trinomial, we're going to most likely be factoring by grouping. First thing we still do is look for a GCF, and all of these terms do not have a GCF, so we're going to factor by grouping. We look at the first 2 terms and the last 2 terms. The GCF of the first 2 terms is 3n squared, and that leaves us with n minus 4. The GCF of the last 2 terms is going to be 2, and we want to still be left with, if possible, n minus 4. Well, if we factor out a positive 2, that will leave us with the n minus 4. We can factor the n minus 4 out in front, and we're left with 3n squared plus 2. Each term is relatively prime to each other. Here, each term is relatively prime to each other, so this is completely factored. Now in this next example, again, there's no GCF to start. So we're going to look at the first 2 and the last 2. The GCF of the first 2 is going to be 2t squared. That leaves us with 4t plus 7. The GCF of the last 2 is going to be 5. And that's a positive 5, so make sure you have that plus sign there. And that leaves us with 4t plus 7. Well, you can see again they have this in common, so we're going to factor that out in front. We're left with 2t squared plus 5. These 2 terms are relatively prime, these 2 terms are relatively prime, so this is the factored form. A few more examples. Take a minute, pause the video, find the GCF first, then factor by grouping if possible. So here we have our final factored version. We factored out a 4q. This is what was left over. First two and last two. When you find the GCF of each, you see that what's left over is the same, so you factor that out. And what's left over, the q squared and the 3, go in the other binomial. Here again, GCF first is 3h. We're left with this. We look at the first two and the last two. The GCF is h squared for the first and 2 for the last. What's left over winds up being the same, so we factor that out. What's left over goes in the other set of parentheses. The 3h stays in front. What's inside is both relatively prime. There's no difference of two squares. There's nothing else we can do, so that's our final answer. So whenever you're factoring a polynomial, first step is always factor out the GCF. If you don't do it in the beginning, you're going to most likely forget about it later on. The second step, if the polynomial has 2 or 3 terms, if it has 2 terms, check whether or not it's dots. If it has 3 terms, it could be a perfect square trinomial or a pair of binomial factors. So this basically means the same thing. If it has 3 terms, we're going to check if it's ax squared plus bx plus c, or if it's just x squared plus bx plus c. If the coefficient is 1, you're just going to set up the 2 binomials. If the coefficient is greater than 1, that's when you either have to slide, divide, and then bottoms up, or use the eyeglass method. Next, if the polynomial has 4 or more terms, you're going to factor by grouping. So if it's 2 or 3, so if it's 2 terms, it's dots. 3 terms, it's either ax squared plus bx plus c or x squared plus bx plus c. And 4 terms, still look for the GCF first, but then factor by grouping. And finally, check. Make sure that there are no common factors other than 1 in each binomial that you have left.